Hi, guys. How you guys doing this morning? So I don't know if you guys have had a chance to see the Canvas page, but I published all the rest of the weeks for the semester. We really only have like 3 weeks left to the semester. It's coming up really quick. We've got this week, right? So we took our test on Monday, and I'm grading them right now, so I don't have much to tell you. And we are starting chapter 3 today. So we're going to do 3.1 today, and I think we'll probably do 3.1 again tomorrow. And then we next week have a full week of classes, so we'll continue on with chapter 3. I'm sorry, not next week. Next week is Thanksgiving. Sorry, we only have one class next week, which is on a Monday. And we also have a quiz on Monday. I want to make sure you guys see that. On Monday, we have a quiz on chapter 3.1. So we're going to do 3.1 today and tomorrow. Okay. And then you guys have homework, questions 1 through 15, which is, it seems like a lot, but they're all kind of similar questions. And then there's classwork for 3.1, which I'll start going over some stuff today on 3.1 for the classwork. Now, there are a lot of problems on the classwork. You do not have to do all of them, okay? Just do like a handful of problems on each page. There are 2 pages, right? I think I couldn't upload, for some reason, multiple documents into my classwork assignment. So on our Canvas page, it has like the classwork 1 and classwork 2 for 3.1. And then the classwork assignment is just like all of them for chapter 3.1. So you don't have to do individual ones for that. I'll see if I can upload multiple documents on that. I haven't had much success with that in the past. Anyway, but please, just a handful of, different problems on, the couple different pages that we have. Do not feel like you have to do the whole thing. There are like a lot of problems on there. They're just practice problems, okay, for classwork. The homework ones, remember, our solutions are posted at the very beginning of our modules page, right? There are homework and solutions for the all of our homework chapters. Okay, but I just uploaded essentially all of the questions for chapter 3, but told you only have to do chapter questions 1 through 15. So don't forget, Monday we'll have a quiz. We'll have like the beginning of class period. We'll, maybe start talking about 3.2. I can answer questions on 3.1, and then we'll probably end early so that you guys can start the quiz if you want. I'll set it up to start maybe halfway through our class if you want, and then you'll have a 24-hour window to work on that. So next week we have only 1 day of classes, which is Monday, and then the rest of the week is off for Thanksgiving break. So you guys are all set, unless I think maybe you have Tuesday classes. I don't know. I don't teach on Tuesdays. And then we come back for classes, and whether or not you guys come back to campus or not, we'll still have classes remotely like this. The following Monday, which I think is November 30th, and then that week, okay, that's our full week, right? And then after that, basically we've got let's see, only a couple class, 2 class periods after that. So when we come back after Thanksgiving, we'll talk strategies for what happens in the last break. I know it's a short break, but we're coming up on the semester break. It's going to be, quite a bit. And just to remind you, we do not have a final exam in the class. We do have a final project. So we'll talk about how we want to do that. When we're in person, typically I do project presentations, but this time I'm trying to think about how we can do that. Maybe if you guys want to talk, maybe we can share screens. Okay, and then we can all spend like 10 minutes, each person sharing a screen where they talk about their work, so we can all see what everybody else was working on. It's actually a really neat thing to kind of see what other people are doing. I'll see about how I can make that work in Zoom. I think that would be fun, but that'll be like our very last class day. Okay. Also, I want to call your attention to we have problem set 3, which remember, like a month and a half, 2 months ago, I posted all of the problem set assignments. Problem set 3 is due on our last day of classes, December 7th, I believe, or December 9th. No, December 9th. I made the problem set due. So make sure you've got that there. I think the problem set itself is under assignments, but I posted it some time ago. Anyway, so just some administrative stuff to think about. All very exciting. But we're nearing the end of the class and the topics. There are only 3 sections in chapter 3, so we have a quiz for each section essentially. So keep that in mind. Stuff that's coming down the pipeline. All right, so let's talk calculus. So chapter 3 is all about calculus and what we're going to be doing. today, chapter 3.1 itself is about derivatives. Okay, so we talk about taking a derivative of a function. We're going to talk about like what that actually means. So this is more in detail. We're going to talk about like a slope of a line. And we always think of y equals mx plus b, where my m is my slope, right? But what if I've got y equals x squared, right? What's the slope of that line? So we need to have a tool for being able to tell what's the slope of a line that I can't just, you know, it's not a straight line. How am I going to do that? So we're going to talk about slopes of the lines, which form the basis for our idea about derivatives. Basically, rates of change. Okay, so derivatives are also a measure of how things are changing in a particular situation, right? And we talk about like the volume of something that's changing, and we talk about the distance between two objects as changing. Derivatives are going to help us get there. We also use derivatives to talk about motion in a plane. This is the thing that's going to be talking about, going to be applicable to you guys when you're thinking about your game design. Okay, because we're going to talk about things like velocity and position and acceleration. And then how do we incorporate that if we want to, like if I've got some kind of object on the screen and I want to make it go at a certain speed, or I want it to, you know, after a certain time period, I want it to accelerate, or I want it to slow down. So these are the things we're going to start to learn. So 3.1 is derivatives, 3.2 is integration, which is the other side of derivatives. So going backwards, it's like the antiderivative. And then 3.3 is like a differential equation. How do I combine derivatives and functions all in one equation? Okay, so let's start from the beginning and we'll think about slopes. So slope of a line, because we're gonna start, I'm gonna assume, I know some of you guys haven't had calc before, or maybe it's been a long time. So don't sweat it when we do this stuff like we did with the vectors and the matrices. I'm going to assume that basically you haven't seen it before. So I'm going to teach you a lot of stuff about what these all mean. So if I've got my axis, my x and my y axis, and then let's say I've got some function, you know, whether it goes through the origin, y equals mx, or, you know, whether it, you know, passes through a line like this, or whether it's, so this is y equals mx plus b, or I could be, you know, going in the other direction. It could be passing down like, here's my other line. Here's also y equals mx plus b, right? Where in this case, my slope is negative, my slopes are positive, right? So the slope is going to tell us stuff about this line. So the slope is basically like, I'm going to draw like a right triangle right here, right? I got a slope here. These are all slopes, right? They're all like a way of taking a look at a slope. So if I think about, let's draw this. Here's my line again. I'm going to take it out of context and draw it here. So here's my line, y equals mx plus b. So here's my right? So in my XY plane, so I've gone over, you know, some delta X value. So I've gone from here to here is some, you know, some difference in X, right? I've gone from X1 to X2, say for example. And then here, from here to here, I've gone a delta Y value. Okay, we often call this our rise. We often call the X part our run, right? I'm running and rising, right? So when we talk about our slope, we say it's the rise over the run, which I always like to think of as delta Y over delta X, which in terms of actual particular points, I can think of as Y2 minus Y1 all over X2 minus X1. Now I did Y2 minus Y1. I could have done Y1 minus Y2 as long as I kept this index and this index. Like I started Y2 minus Y1, that means my X has to be X2 minus X1. They have to be consistent, okay? So this is gonna be, say I've got, here's Y2, here's Y1. So I'm gonna go Y2 minus Y1. Here's X2, here's X1. So this run is gonna be X2 minus X1. Right, so we're looking at the difference in values, right? So we're kind of thinking about, and that tells us, you know, how much things are changing in our function. Are changing. So, and I think about that, how much they're changing. I think, well, X is my input. So as I input more in the X, how much is it changing in the Y? So I can ask myself this question: as I input X values, how much in the Y is the function changing? It's kind of like how I think about it, right? For all my input, how much is, so if I input a little bit and then I get a lot output, that's a really steep slope. But if I input a little bit and I only get a little bit of output, that's a very shallow slope. So it's going to tell me stuff, right? If I input a little bit and I lose things, that's a negative slope, right? So these all things tell us all about the slope of the line. And we're talking about, these are straight lines here, okay? So, so let's see. Let me think about how I want to do this. So now those are straight lines, but let's say I have a curved line, like say y equals x squared. Oops, sorry, you can't see what I'm writing. Here's x, here's y. So let's do our parabola, y equals x squared. Right, so here's our axis, here's our, and now I say, what's the slope? Well, now it gets more complicated. So the slope is a more complicated idea. Right, I can't just pull it out of the equation. So this here, m, from my equation, m is my slope, right? I could just yank it right out of my equation. But here, if I've got y equals x squared, there's no one m I can just yank out. So slope is a more complicated idea. What this means is we measure the slope at a particular point. And in particular, we look at x equals some value, which, you know, I'll call x naught. So what can happen is I'll say I've got this x naught value and I go up to my graph and I say, what's the slope on that x naught value, right? So I look at this, right? And I'm going, okay, so what I'm going to do is I'm going to superimpose a straight line on top of that. Y equals mx plus b. That's my line right here. And this is going to have a particular slope. Okay, and it's the slope at this point, x naught right there. Okay. Now, what that slope is going to tell me is, how is this function y equals x squared changing at that particular point, x naught? So slope tells us how our function y equals x squared is changing at a particular point, x naught. And this is where the derivative comes into play, okay? Because my derivative of our function, right, is my slope. Is our slope. Now I can come up with a generic derivative, you know, y equals something, and then I can plug in my x naught to tell me what is the slope at this point. So I'm going to use our derivative at a particular point, and I'm going to just use my x part of that at a particular point, x naught, to find the slope at that point. Now, why do I want to do that? Because the derivative is going to tell me stuff about my function, right? I'm going to get value for my derivative, and based on that value of the derivative, it's going to tell me, is this function increasing? Is it decreasing? Is it increasing really fast? Is it decreasing really fast? You know, what's happening, right? So the derivative is a very powerful thing, okay? So let's talk about like how we're going to calculate that derivative. Hang on just a second. Sorry. Okay, so let's talk about how we're going to define our derivative. Okay, so our definition of our derivative, how we're going to set that up. So I can say, right, I've got this function, f prime of t. This is my derivative, right? And I'm going to say, basically, I'm dealing with, I've got a change in y over a change in x. So I've got my function, right, evaluated. I'm going to write it down, and then we're going to actually talk about it. Let's say x plus h minus f of x all over h. So let's talk about what's h and what's x and all that kind of stuff. So say I've got some function, looks like this. Here's my function. We call it a function of x. This is the same thing as y is a function of x, okay? So now I look at, here's x right there. And then what I'm going to do is I'm going to add some value. This is x plus h. H is just some, it's just some number, right? I'm going to start off with here. And what I'm going to do is I'm going to take the slope of the line between these two particular points, right? So remember, right? So this is delta y is equal to my function at x plus h. So this is f of x plus h minus f of x all over my change in x, right? So this is going to be x plus h minus x. So it comes out to be f of x plus h minus f of x all over h, okay? And now the goal is I want to bring this h down really, 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 really small to find out what's my point, what's my derivative at that particular point. Okay, so this is velocity. This is, you know, just sort of generically speaking, but we're going to use like velocity and position and stuff to help us with that. Okay, so now we want to make this space smaller and smaller, right? This space right here, this space from here to here, because ultimately I want to get just a derivative, just a tangent line at that spot, okay? So we do what we take a limit where you say our derivative, it's a limit as, this is, we would call this as h goes to 0. And I'm putting out more information on here than you might need because we're going to be using this in chapter 3.3. So I want to kind of give you this stuff here. So this is our definition of the derivative. So we call this df dx. We call it f prime, df dx. It's the same thing, okay? And this is the limit as, we can think of it as, sorry, I'm calling it h, but what it really means is like a delta x. Delta x goes to 0, right? Because I'm changing, I'm like adding that little delta on x of f of x plus delta x all over delta x. Okay, where h, we used h equals delta x before. Okay, and h was just a variable that we use. This is more, you know, details about, you know, what the derivative is, but I wanted to give you some kind of background, like why are we doing all this stuff with the derivative? Because it's important. And also we're going to need this in chapter 3.3 when we actually do it. Plus, you know, I'm going to give you shortcuts for taking the derivative, but you want to know really where it comes from is really just a slope calculation. But I'm doing this, I'm calculating a slope, and then I'm going to decrease my delta x, my h, by just a little bit. Calculate another slope, decrease my h just a little bit, calculate another slope, decrease it, decrease it, decrease it, until I'm basically sitting right here on top of x. And I just want that one, what we call a tangent line. So the red line is what's called a tangent line. A tangent line. And it looks like you can't see that very well. Let me write that better. a tangent line. Okay. All right. So I'm going to give you some, I'll give you some shortcuts in a minute, but let's talk about, let me also just relate to, so first off, let me just tell you too, our position, if I have a position function, we usually call it x of t or p of t, p for position or x of t, you know, depending on what you want. These things, often they can end up being like vectors because I have an x and a y component to them, okay? But my position, right, is where I'm at in space, right? We've been talking about vectors, like where am I at in space? When I think about velocity, is our derivative of position. And it goes like this, right? So velocity equals the derivative of our position. Now, how I think about it, what's our derivative? Our derivative is a slope. This is the change in position all over the change in time. Okay, so my velocity is equal to, I would call it, it would be like delta p of t all over delta t, right? So we're looking at the change in position over change in time. You can think about like meters per second, right? Or feet per second. Those are our units of velocity. Okay, so we're taking the derivative of our position to get our velocity, okay? So if position's a function, I take its derivative to get the velocity, okay? Okay, so our lecture examples for 3.1 is a pretty long, you know, packet. There are a lot of different examples because there's a lot of stuff going on in 3.1. So I'll take a look at here. Now we often, by the way, talk about velocity and position in terms of x and y. So let me just write this because you're going to need this for, right? So if a stone is thrown from a cliff, like say I've got some kind of stone and it's thrown from a cliff, or it falls from a cliff and then it drops to the ground. We're going to do this example in a minute. Drops to the ground, right? And so we've got our x position, and oops, sorry. We have our x position, right, which tells us how far out from the cliff it's gone, and we have our y position, which is how far down it's just going. It's just our vertical. And this is our horizontal. So we often break our velocity up into components that are vertical and horizontal components. When we think about our vertical velocity, we think about things as they relate to being affected by gravity, right? So when I go horizontal, I'm not thinking about things being affected by gravity, but my vertical velocity is going to be affected by gravity. So let me just write out velocity and position, and also acceleration. We're going to talk about that later. Acceleration are often vector functions, right? Where I have, you know, my velocity, I'll have an x and a y, and if it's in 3 dimensions, I'll have a z, okay? But in this case, we just have an x and a y, okay? So let's think about how we want to do it. All right, so this one, example number 1, we're just going to work things through. The examples are going to help us. If a stone is released from a cliff, its vertical position is given by t squared. Okay, so we're thinking about, right, if I just draw it out, my vertical position. So x, y, it's going to be t squared. Although I think it should be like minus t squared because we're going this way. Yeah, it's gonna, we're writing it, t squared looks like this. This is t squared, but in reality, like as it drops, it's gonna be like a parabola going this way, going down. Okay, so what we wanna find out is what is the vertical velocity? And if it hits the ground at t equals 10, what's the velocity in that just nanosecond right before it hits the ground? Okay, when I say what's the velocity as it hits the ground, it's not going anywhere once it hits the ground, but we wanna think about what's the velocity just as it hits the ground. Okay, so let's think about it. So to do part A, I have to think about my derivative. Okay, so I'm going to be derivative of velocity. We're just going to be doing vertical, right? So I'm going to say I've got my dt. So I'm going to go change in my function all over change in time, because this is happening as a function of time. So my function here is x of t. So I'm going to go dx dt. So this is my change in position over change in time, which I'm going to say the limit as delta t goes to 0 of x of t plus delta t minus x of t all over delta t. So now I take my function t squared and I plug in t plus delta t. So this is the limit delta t goes to 0 of t plus delta t squared minus t squared, right? This is my function, and this is all over delta t, okay? So now I have to FOIL this out and then combine terms, right? So once I FOIL t plus delta t, so I'm going to get t plus delta t. Remember your FOIL. FOIL means first, so I'm going to go t squared outer plus t delta t inner, t delta t, and then last, right? So I'm going to put that here. So this is going to be limit delta t goes to 0 of t squared plus, I'm going to combine t delta t plus t delta t is 2t delta t squared. And then I have to subtract out that bit. This piece here should always cancel out. If that doesn't cancel out, then probably you did your algebra a little bit. By gravity, you mean by game gravity, not the actual, so that's a great question. So your gravity in your game, you can define as anything you want. We're typically, when we do examples, some examples we're going to use real gravity, like minus 9.8 meters per second squared, or we're going to use fake gravity. I'm going to say gravity is only 2. Because you want to see how it changes, right? I mean, in your game, your gravity is going to be what you define it to be. You want it to be like Earth? Do you want it to be like Mars? Do you want it to be like, Jupiter? Whatever. It's going to be for you to define. So this is going to cancel with that one. Limit delta t goes to 0. So now I can factor out a delta t. So I'm going to get 2t plus delta t all over delta t. This cancels. And now I can just substitute in delta t goes to 0 into here. So that goes to 0. And this thing is equal to 2t. So 2t is my derivative, okay, of t squared. Okay. So now, what is the vertical velocity? Now I can use my initial conditions. Use your conditions to solve. Okay, so now when I very first start, my vertical velocity is 0 because the ball hasn't been dropped yet, right? So initially I'm at 0. And so at t equals 1 second, right, I've got a velocity of 2, okay? And also when it hits the ground at t equals 10 seconds, I have a velocity of 20. And this is, they didn't give me units, so it would be like meters per second, or let's just write it in meters per second. They didn't tell me, so I'm going to assume it's in meters. Okay, so I'm going to get v of 10 is 20 meters per second. This is actually the answer for part B right there. Okay, so this is my velocity, 2t. Okay, so now I can take whatever time I'm looking for, and I can plug in time, t equals 0, t equals 1, t equals 10, and find out what's the velocity, okay? This is a pretty detailed example. We're using the definition of the derivative to help us solve it. As we go through, I'm going to start teaching you some shortcuts. The shortcuts all come from our definition of the derivative. You don't have to go through this long stream of things every time you need to take a derivative. We're going to talk about certain rules that are going to be shortcuts to this definition, okay? All right, so let's talk about our shortcut rules. Shortcut rules for taking the derivative. So I don't have to go through that whole limit each time, right? So I can make up a table of what my function is, and I'll call it f of t. It could be f of x, could be f of whatever variable that we're looking for. And then I'm going to talk about what its derivative is. Okay, so my function, f of t equals a, where a is a constant. Let me write that down. This is a constant. Okay, when I go to take the derivative of a constant, right, any derivative of a constant is equal to 0. Okay. I have an like a polynomial function, t to the a. This is like x squared, say for example. It's just like x squared, say for example, right? So what happens, this is called the power rule. I take my exponent, I bring it down. I repeat my variable and I subtract 1 from the exponent that was there. Okay, this is called our power rule. Power rule for taking derivatives. We're going to go through some examples on this stuff too so you can see, but I just want to give all the rules to you first. Okay. Trig, you want to have, so sine of t. When I take the derivative of sine, I get cosine. When I take the derivative of cosine, I get minus the sine. Sine and cosine, they're both basically the same waveform, only they're just shifted by 90 degrees, okay, which is why we're looking at one of them's positive, one's negative. Okay, because one of our slopes is positive, one of our slopes is negative. Okay, so e to the t. When I go to take a derivative of an exponential function, e to the t is exponential, I get the function back. Okay, if I take the derivative of the natural log of t, I'm going to get 1 over t. Okay, so some functions, some rules. I'm just throwing it out there. Don't worry if you haven't seen it before. We're going to be practicing this stuff, like right now on our lecture examples. Okay, let me give you guys a chance to finish writing that down. Okay, so lecture example number 2. What's the derivative? Let me make sure, I don't think this is in focus. There. What's the derivative of f of x equals radical x? Radical x doesn't seem like it was a part of one of the functions we talked about, but it is. I'm going to rewrite this. So f of x equals x to the 1/2. Any kind of root that I have, right? So if it's the nth root, I'm going to say, I can write this as x to the 1 over n. Okay, so I'm doing that here. F of x equals x to the 1/2. Well, this is the power rule for taking derivatives. So my derivative, f prime, I take my exponent, bring it down out front. I subtract 1 from the exponent that's there. It's going to be 1/2 times x to the 1/2 minus 1 is minus 1/2. Anytime I have a negative exponent, that means this thing needs to be on the other side of the dividing line. 1/2 times 1 over x to the 1/2, which is a way of saying 1/2 times 1 over radical x, or I could write it as 1 over 2 radical x. And that's my derivative. Okay. Now, f of x equals radical 2. Radical 2 is a constant, right? So my derivative is just equal to 0. Derivative of any constant is equal to 0. Okay, example 4. What's the derivative of f of x equals 1 over x? Okay, so this I'm going to rewrite like this. X to the minus 1. So this is 1 over x to the 1, right? If I write it like this, this says this x needs to be on the other side of the dividing line, 1 over x. I like to do it this way because I'm going to use the power rule. Right, so when I take the derivative, I'm going to take my exponent, bring it down out front, take my variable, I'm going to subtract 1 from the exponent that's already there. So I'm going to get minus 1 times x to the minus 2, which is equal to minus 1 all over x squared. Okay. All right. A lot of great examples here. So we have some other rules that we're going to do. So I'm going to give you a rule and then we'll do an example. All right. Right, we talked about actually the power rule. That was one of our rules. I'm going to give that to you again. Actually, no, I'm not going to give it to you. I'm going to give you other rules besides our power rule. So the first rule is called linearity. And this basically means if I've got f of x equals g of x plus or minus h of x, and I want to take the derivative. So then f prime of x is going to equal to g prime of x plus or minus h prime of x. Okay, so all I'm doing is taking the derivative of each individual function. Think about your polynomials, x squared plus 2x plus 1. I want to take the derivative of that. I take the derivative of each individual piece, and I add or subtract all those pieces back up together. Okay, so that's my linearity. So let's do our example here. Example 5. F of t equals 2e to the t. Let me make sure I'm doing, yeah, 2e to the t plus 3 radical t. So I want to take this derivative, right? Which means I'm going to take the derivative of this and add it to the derivative of that. Okay, so I'm going to go derivative of 2e to the t. Remember we said about, this is like e to the t is just e to the t, right? So this is just going to become 2e to the t plus 3 times, I'm going to do this derivative. So this is going to become 1/2 t to the 1/2 minus 1. So this is 2e to the t plus 3 times 1/2 t to the minus 1/2, right? Which is 2e to the t plus 3/2 times 1 over radical t. Okay, part B is a little easier, right? I want to find y prime, that's my derivative. So I'm going to take y prime is going to be the derivative of each individual piece put together. So I'm going to go, if I've got a constant, I'm going to do the power rule, 2x to the 2 minus 1 plus 2. This is also the power rule, but we're multiplying 2 times 1 times x to the 1 minus 1. I'll write it out like that. Plus 0. Remember, our derivative of our constant terms are 0. So let's multiply this out. So 3 times 2 is 6. 2 minus 1 just becomes x to the 1. Plus 2 times 1 is, so x to the 0, x to the 0 is equal to 1. So this just becomes 2. And I don't worry about the 0 anymore. 6x plus 2. Okay. Our second rule that we want to think about is what we call a product rule. Okay, so linearity was when I was adding or subtracting two functions together. The product rule is when, let's say, f of x equals g of x times h of x. It's the product of two functions, right? So if I want to find the derivative, what do I need to do? What I do is I take the first function times the derivative of the second plus the second function times the derivative of the first. So let's write that down. I'll write it in green. First times derivative of second plus second times derivative of first. And it doesn't matter, you know, what order you go in, okay, because we're adding, right? So I could do the second times the derivative of the first plus the first times the derivative of the second. It doesn't matter because we're adding. So that's our product rule. Okay. Example 6, we're going to do the product rule. Okay, so I've got a function, first function, second function. My derivative, f prime, is going to be the first, t, times the derivative of the second, cosine of t, plus the second times the derivative of the first. So my derivative is equal to t cosine of t plus sine of t. Okay, this one, part B. My first function is x squared. My second function is e to the 2x. E to the 2x is a trick. We haven't learned the 2x part. We're going to do that in just a minute, but let's go ahead and do this. So y prime equals my first, x squared, times the derivative of the second. So this is, when I do the chain rule, I repeat my exponential and then I take the derivative of the 2x. I've got a 2. Plus the second, e to the 2x, times the derivative of the first, 2x. Don't worry about this. This is the chain rule. I snuck that in there. We're going to do that rule next. Okay, so let's clean this up. So y prime equals 2x squared e to the 2x plus 2x e to the 2x. And you can leave it like this. You don't have to factor out stuff. Okay. So that's our product rule. Two functions being multiplied together. Is this solely going to get applied to the stuff we did in chapter 1 and 2? No. Sort of, not really. So what's going to happen is this. So in chapter 2, we talked about transformations, right? Where we moved, we rotated, we reflected, we did a bunch of stuff, right? Chapter 1 was building up like nomenclature and ideas about projections, lines and planes and things like that. Chapter 3 is adding a level of dimension to things where I'm going to add, basically, we're going to apply this to things like velocity and acceleration. So you can think about, as I rotate an object, my position in space is given here, but maybe my velocity, maybe I want to have a velocity component. So the velocity is going to increase as I rotate, right? So it's going to rotate, you know, as I go, it's going to get faster as I go. And so you want to have a certain, you know, velocity for how you're moving things around. So that's how you're learning the skills for how you can add things like velocity and acceleration to the work that you're doing. Okay, but we're not necessarily going to take projection. We're not going to project it really fast or slower. We're going to talk about what does it mean to do velocity and acceleration. Okay, all right. That was the product rule. So let's talk about quotient rule. Okay, so quotient rule. So quotient means division, right? So in this case, I would say my function f of x is equal to h of x over g of x. So I've got a function in the numerator. So we're going to work with calculus and Euler quaternions. I'm just teaching calculus. So chapter 3 is just calculus. How you want to apply it to your rotations and your reflections and your projections is going to be up to you. You can think about your as you rotate an object through space, or as you do something, you're changing its position. Okay, do you want to change its position at some constant rate as you go, or do you want to make it go quicker or slower? How fast do you want this to actually happen? You can add a velocity component or an acceleration component to what you're trying to do. Or if you have an something that's dropping from a like, you know, dropping from the top of a building or something like that? Do you want it to drop with a certain level of gravity? You know, how fast do you want that to actually be, you know, displayed on the screen? Because like we know, you know, like the computers can do these computations very quickly and it can put things up on the screen, but how fast do you want it to go? It's going to be determined by your velocity and your acceleration in your particular world. So how long do you want the computer to wait before it puts that up on the screen? Okay, so our quotient rule says our derivative is going to look like this. I go the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so let me write that down in words. So this is bottom times derivative of the top minus the top times derivative of the bottom all over whatever the bottom function is squared. We square it. Okay, so our quotient rule says to do that. Okay, example 7. So f of t equals t over t squared plus 1. So when I want to go find my derivative, I take the bottom t squared plus 1 times the derivative of the top minus the top times the derivative of the bottom 2t all over the bottom squared. We can make it look a little bit nicer. So this is going to be t squared plus 1 minus 2t squared all over t squared plus 1 squared. Okay, I can clean this up too. So this is going to be t squared minus 2t squared. This is going to be 1 minus t squared all over t squared plus 1 squared is our derivative. You could also have left it like that. Part B, 3x plus 1 all over 2x squared minus 5. My derivative, the bottom, 2x squared minus 5 times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so this looks like 6x squared minus 15 minus 12x squared minus 4x. 2x squared minus 5 squared. So this 6x squared minus 12x squared minus 6x squared minus 4x minus 15 all over 2x squared minus 5 quantity squared. Okay, all I did was combine like terms right here. Okay, quotient rule. Okay. Chain rule, I snuck that in on one of the examples. Now we're going to tell you what it is. So chain rule happens when I have a function that's inside of another function. So imagine that I had f of g of x, right? My inside function, when I go to take that derivative, let's call this y equals. When I go to take that derivative, I got to take into account the derivative on the inside function too. So my derivative is going to be f prime of g of x. So I take the derivative of the outside function times the derivative of the inside function. So this is derivative of outside function, right? With that inside function still there, times derivative inside function. Okay. Chain rule, it's very powerful. We need to take into account all those other extra functions on the inside. Okay, so I've got y equals sine of 4x. You can kind of think about 4x is my inside function. My derivative of the inside function is just equal to 4, right? So keep that in mind, because what I'm going to do is when I go to take the derivative, I say derivative of the outside function. So derivative of sine is equal to cosine. So it's a cosine of 4x times the derivative of the inside function times 4. So I'm going to do this. This is going to be 4 cosine of 4x. I need to put this 4 in the outside because it's just a multiplier of my cosine. It doesn't get multiplied by the 4x anymore. The 4x stays inside of my cosine. Okay. This one's a little more complicated. I've got 1 over t. That's my inside function. What we've been calling our inside function. So the derivative, we did this with the power rule, right? So this is, derivative is going to be minus 1 over t squared. That was our power rule. We did this one before. So now when I go to take this derivative, I do the derivative of the outside. So derivative of e to anything is just that function repeated itself times derivative of the inside function. So I'm going to put it all together. I'm going to put this, usually I put the multipliers of the exponent out front, minus 1 over t squared times e to the 1 over t. Okay. Wasn't there a function like f of x equals g of h of x? Yep, that's our chain rule, g of h of x. That's right here. That's our chain rule function. So we're doing chain rule right now. So this is f of x is sine of 4x, right? And sine, and then 4x is our h of x. So f of h of x, so sine of 4x. So 4x, it doesn't look like a function, but 4x is a function. Okay. There's a lot of information coming at you today. Let's do one more example. I'm going to overload you with one more example, just so you can kind of see how we can put this together into, into like a sort of a word problem. Okay, so at noon, ship A is 8 miles north of ship B and is steaming south at 16 miles per hour, right? So let's draw a picture. So I've got, here's ship A, and it's north of ship B, right? So here's ship B. And then A is coming south at 16 miles per hour. Ship B is headed east, which is this direction, at 12 miles per hour. Okay, find their distance as a function of time and find the rate of change of the distance as a function of time. Okay, so I need to think about what's going on. So I like to do this because it's going to help me set up like a coordinate system, and I'm going to use that to help me figure out my distance is going to be like my distance formula. Right, so I can think about x of A, y of A is my position of A. And I've got x of B, y of B is my position of B, right, of my object B. Okay, so my distance formula says I need to subtract my x's, xa minus xb squared plus ya minus yb squared, and then take the square root. It comes from the Pythagorean theorem, right? You can think about it like this. This is xa, ya, and this, my b is moving this way, right? So this you can think about, this is xb, yb. Because at time they're here, but then they go like that, right? So then what's their position? So this is their distance as a function of time. Okay, so we need to plug things in. All right, so now let's think about, but I was given like miles per hour and not actual coordinates. So I've got to be thinking about what's going on. So now let's think about A, right? So we were just given 16 miles per hour due south, which means that it's affecting the Y position, but not the X position, right? So remember our velocity, miles per hour is a velocity. This is our distance divided by time. right? So if I'm looking for distance, I want the distance on everything. So I'm going to solve for distance here. So distance is equal to velocity times time, right? And for time, I don't know what time, I'm just going to call t, just call it t as a variable. Okay, so now in my x direction, my x position on A isn't changing ever. It's always 0, right? Because I'm just going due south. Okay, so it's always 0 on A. And now, but my y position is changing like this. So I start here. Let's see, it's 8 miles north. So I start off at 8. This is an 8. So I start off at 8. And I'm going to go subtract it, 16 miles per hour times time. So 16 times time. So this is my A. Okay. I'm going to do the same thing for my B. So this starts off at 0 and it goes east at 12 miles. Okay. So now B, we're going, what do we say, 12 miles per hour due east, which means that we're affecting our x position, but not our y, because we're just going straight horizontal, just going due east. Okay, so now what I want to think about, right, this is 12 miles per hour, so I'm going to go velocity times time. I start off at 0, right, so this is going to be 12 times time, and then I'm not going anywhere in the y position on B. Okay, so here's A, and then here's B. Okay, so now I want to be able to put those together. Okay, so let's write that down again. So I'm going to say A. We said A was 0 and 8 minus 16t. And then B is 12t and 0. So now I need to do my distance formula. Remember how we did our distance formula before, where I'm going to go x sub A, or I'm going to go x sub B minus x sub A. It doesn't matter because I'm going to square them, right? So this is going to be delta x squared plus delta y squared, square rooted. Okay, so a change in our x and our change in our y, and it's going to give us our distance as a function of time. So now let's write this out as, I guess I'll do x sub A minus x sub B. So I'm going to set this up where I'm going to go 0 minus. Okay, so when we change the x's, so I'm going to go, let's see, 0 minus 12t squared plus this here, 8 minus 16t minus 0 squared. Add them together and square root it. Okay, so this is going to be minus 12t squared. So this is 144t squared. Plus, this is going to be 8 minus 16t quantity squared. I've got to do a FOIL on that. So let's do that offline. So 8 minus 16t, 8 minus 16t. So this is the first. So 64 minus 8 times 16t minus 8 times 16t. Minus minus is plus. 16 times 16. 256t squared. Okay, so let's put these together. So I'm going to get 144t squared plus, right, this whole thing. So it's going to look like, let's see if I can get this right. Let's see, 64. What's 8 times 16? 8 times 16 times 2. Good. Minus 256t. And then 16 squared plus 256t squared, square rooted. Okay, now we get to combine all the like terms, right? So what we're going to do is I'm going to go 144 plus 256. So 144 plus 256 is going to give me 400t squared minus 256t plus 64. And this gives me my d of t. Okay, I think I can factor out, looks like I can factor out a 4. So if I factor out a 4, I'm going to get 100 t squared minus 64t plus 16. It doesn't matter if you want to keep doing that. I'm sorry, I can factor out a 16 out of all of this, which I can factor out another 4. So if I factor out another 4, here I'm going to get 25t squared minus 16 plus 4. So my distance is 4 radical 25t squared. Whoops, there's a t. 16t plus 4. There's our distance as a function of time. Okay. Next time when we start, I'll pick up from here and we're going to find the change in distance as a function of time, which is our derivative. We'll do that next time. Okay, guys, I know there's a lot of information to take in, but we're just going to work through. And then when we meet up next time, we will have time to do some classwork problems too during class. Okay, all right, you guys. Have a great day.
Thank you.
Take it easy.